Hello, everybody. Can you hear me? Yes? No? Thank you. Well, it's good afternoon now. Thank you for coming back. I'm delighted to be chairing this conservation session. So we're going to hear from experts exploring innovative approaches to preserving cultural heritage. My name's Barrett. I'm the Imperial College Archivist and Corporate Records Manager and a member of the search committee. And so I'm on the cultural side of heritage, but I really love learning about the scientific, technical side. And I hope you will also enjoy learning from our speakers. And our first speaker is Kate Jennings. Kate is subject leader in metals at Westdean College, and she will present on craft science and collaboration in the conservation of cultural heritage. She'll be highlighting the interdisciplinary efforts that drive successful conservation projects. So please join me in welcoming Kate.
Hi, morning everybody. Hopefully my microphone is working and I can advance the slides. There we go, perfect. So, as Anne mentioned, I'm going to be talking today about craft, science and collaboration in conservation. And I'm really excited by the amount of times craft has already been mentioned this morning because I thought I might be an outlier, but I'm not, so that's very, very fortunate for me. So I'm just going to introduce myself before I get started on the main part of my presentation. I teach the metals courses at Westdean, which includes a blend of making and conservation courses. I trained as a blacksmith before I converted to conservation, but I never really left forging behind because once I finished studying, we started a small business which was focused on architectural metal conservation, but we also made new objects alongside our conservation practice. So I've always bridged craft and conservation, and now that I teach, it's become really important to figure out how to articulate and make the most of that relationship. It's starting to become a much bigger part of my practice, and so that's what I'm going to talk to you about today. So the main takeaway for this talk is going to be what the collaboration between craft, conservation and science can achieve. And I'm going to try to substantiate that by talking about a particular example of a research project that I undertook with some scientists from Winterthur over in Delaware. And there really is nothing better than working with scientists because they give me so much knowledge, which I love. But before I do that, I need to talk about craft a little bit more widely. And that's because I need people to understand what I mean when I use the word craft. So 3 main areas for this talk. We're going to talk a little bit about what conservators think craft is and why that matters, or what conservators tend to think craft is and why that matters. We're going to talk about how else we could possibly characterize craft, and then I'm going to talk about this example, which I've mentioned. So, first question. What do conservators think craft is? And this matters because how we define something ultimately will define our expectations about what that thing can or can't contribute to our ability to achieve our goals, the conservation of cultural heritage in this case. So that brings us to the first challenge in how craft is integrated into cultural heritage and conservation, which is how conservators tend to understand craft. And when I say conservators here, I really mean Anglo-American conservators because there are quite notable differences between how Nordic conservation and how East Asian conservation thinks about craft and integrates it into conservation. But that would be the topic of another talk. So I've already carried out some research on this point, and the first piece of research I'm going to refer to is a survey of the South Region Conservators Network, which I carried out in February 2024, and the members were kind enough to really engage with this survey. I asked them 19 questions in total, which were a mix of Likert scale and open-ended questions. I'm only going to mention responses to one of these questions today, which was, what words or concepts do you associate with the term craft? We had 34 respondents whose responses I went through and manually coded to identify what themes emerged. People could write as much as they wanted in response to this particular question. So just as a preemptive note for anyone trying to do maths, the maths doesn't add up on this because it could be coded to like 4 different categories. A lot of the responses received indicated quite a common perception around craft being primarily a physical thing. If I pop some arrows in, you can see that 4 out of the 7 themes link into the physicality of the types of actions or work associated with craft in some ways. Examples of the responses coded to these themes on hand-based manipulation were things like hand skills, hands-on, handmade, hand tools, hand-eye coordination, manual dexterity, dexterous dexterity. So really like very physical, kind of hand-oriented ways of thinking about craft. Skill doesn't always have to be linked with physical action, but in this case, the types of terms it mentioned again were things like hand skills, hand-skilled sort of applications of tools, and then making obviously is a very physical act generally when associated with craft in particular. And again, it was things like handmade, making something physical, making something from scratch. And even technique tended to include a sort of physical element to it, like hand skills and techniques, exploring material, exploring technique. So quite a physical kind of theme coming through out of those. But also things like creativity, being creative with materials, and then starting to get into things like material-based insights that can be generated as a result of these physical interactions with materials, which is where it gets really interesting. So understanding of materials and how they work when new, exploring material and technique, knowledge of how a material handles. And then the other way that we can sort of get an insight into how conservation as a field is thinking about craft is from literature reviews. So I had a look through the Journal of the Institute of Conservation, which published 32 articles between 2009 and 2024, which featured the word craft. 17 of them were only using craft to describe a historic making technique or supplies, by which I mean they were doing something like describing the evolution of Korean craft bookbinding practices, or the use of craft glue, or the use of craft envelopes. But the other 3 themes were quite interesting, so we're going to have a look at some samples of the types of, the types of contexts in which people mentioned craft. So here we're thinking about craft's place in conservation. So in this case, Irene Brukel had written about how she thinks that craft skills need to rest on a solid scientific scholarly foundation which offsets them from an art or a craft, which is kind of one end of the spectrum of how conservators often seem to think about craft. Craft doesn't really hold a value in and of itself, and instead has to be validated in some way by association with science and scholarship. At the more positive end of the spectrum, we can see that craft seems to be viewed as part of a rare skill set, which is important in conservation, but then there isn't really any more depth to how they interrogate craft beyond that point of just saying they think it's important and rare. In terms of craft's role in conservation education, this is a quote from an article by Jane Henderson on university teaching and the development of conservation professionals. And I should say it's balanced with an equivalent awareness of the potential shortcomings of academic contexts. But despite this awareness, I think Jane's comment on what she thinks is likely to be the focus in a craft teaching context is interesting, because it allows us to start identifying what quite often comes through in discussions about what craft is and what it does, which is this very instrumental kind of mechanistic functionality. And then finally, there are only 2 articles which attempted to sort of define craft, and one of them was by Hannah Hurling, and I think Hannah Hurling makes a great point here, and it's because she's incredibly articulate, and it's this point about craft being about revelation, because this really starts bringing us to a more considered position on what craft can do, which is generating insights through making and manipulation rather than analysis and testing. So it's just a different way of generating insights. So how else can we perhaps characterize craft? And I would say here that actually craft can be a really systematic research practice in its own right, but rather than being based around testing in the way that people tend to be used to in perhaps a more scientific setting, and my insight on that front is limited, but it's really about using your own body and your cognitive processes as an integral part of testing and working, being able to understand what's going on with objects and materials that you work with, at an almost sort of subconscious level, but also reliably repeatable level, because if you had to process all of the inputs and variables consciously every time you work with objects, it would take you a day just to identify all the variables. So instead, you have to build this kind of reliability and how you can understand and manipulate your materials so that you can be sure of the outcome before you even start. And people call these ways of working by a few different terms, but the ones that we tend to see popping up repeatedly are things like situated perceptual experience, tacit knowledge, and embodied cognition. And I think these are all things that we should be talking about when we talk about craft. So we've been a little bit philosophical there. Now we're going to go to a slightly more tangible example. And this is our problem, which we're dealing with. What you can see on screen is an oil lamp from Winterthur Museum in Delaware. And you can see on one side it looks quite discoloured, whereas on the other side it looks more like you would expect a silver-plated lamp to look. The reason it looks discoloured on one side is because you're looking at a quite degraded cellulose nitrate-based lacquer. Winterthur have about 12,000 pieces of silver in their collection, and they're all lacquered, just about. And they've been monitoring their condition in quite a lot of detail over quite a long period of time. And as a result of this, they've actually noticed something really interesting, which is that cellulose nitrate lacquers tend to deteriorate faster on Sheffield plated silver than on electroplated silver. And for anybody who is now wondering, what is the difference between Sheffield plate and electroplate, let me enlighten you. So, first we're going to talk about electroplating because it's probably the best comparator for most people. Apologies to all of the scientists and engineers who are going to be upset with my description of electroplating, but basically it's a process where you use electricity to pull metal out of a liquid solution and deposit it on another surface. And the reason why you do that is quite often for an aesthetic purpose, to make cheaper metals look more expensive, like silver plate and copper, to improve corrosion resistance, or to modify the physical or chemical properties of a surface for some other reason. There's a lovely set of images on the right-hand side of the slide as you're looking at it, which shows some of the equipment and processes used for carrying out this electroplating process back in 1852. Another way that people used to achieve the same end goal of making cheaper metal look more expensive was the Sheffield plating process, which instead of using electricity to bond one type of metal to another, used heat. So if you have a look at the photo in the middle of the slide, this shows a roll and manufacturing sequence for Sheffield plate, which is in Sheffield Museum. Manufacturers who used this process would take a chunky ingot of brass or copper or nickel silver and a thinner sheet of silver, and they would use heat and pressure to fuse the silver to the top of the copper alloy ingot, and they would then roll that ingot out to the desired thickness and make objects like candlesticks, lamps, teapots, anything you can imagine really. The time period that Sheffield plate was being made was roughly 1740 through to 1840, although not always clear delineation. No one has commercially made Sheffield plate since about the middle of the 19th century. There are very few records about the process, and what records there were mostly written quite a long time after Sheffield plate had ceased to be made, and by people who didn't make Sheffield plate, but just were interested in collecting it. So, quite a lot of very practical information lost, and there's actually a great quote from one of the books about Sheffield plate, which I'm going to read you because it captures the rest of the process I'm about to describe really nicely. It will be found that the processes of most handicrafts are fundamentally simple, and old Sheffield plate is no exception, but its simplicity begins and ends with mere description. When it comes to actual practice, that is another matter, and what may be described in a few words will take years of constant practice to acquire the sleight of hand necessary to the exercise of the craft. So, first thing we had to do, we didn't actually have to do it, but we wanted to do it for, the full process, was to make our substrate metal, which was basically a brass. And the records that are available indicated the go-to recipe was 17.5 pounds of copper to 3.5 pounds of brass, although with no indication as to what percentage of zinc was in the brass. There has been some XRF testing on one piece of Sheffield plate where the brass substrate is showing through the silver plating, which revealed that was actually a 5% zinc brass. So that was what we ended up making. There are a lot of questions, a lot of iterations of testing to work through on everything from whether to start from pure zinc and copper, or whether to start with brass and copper, what type of molds to make, lots of different things. We really struggled with porosity to begin with. In solid moulds, you can see there's a couple of grey arrows pointing to the moulds, which we poured our liquid metal into. The solid one, which is a little flat one, really bad porosity, probably because all of the dissolved gas in the molten metal couldn't really escape very well. As soon as we switched to sand moulds, which is what's in the middle picture, no problem with porosity. So, 12 ingots later, we had a really nice ingot, and lots of failed examples to run other tests on later, perhaps. Next challenge was fusing the silver plating to the surface. And this was a really interesting challenge because we were trying to target a silver plating thickness after we rolled it down of 6 microns. So quite a small measurement to be working with quite large scale processes. Generally, the thicknesses of silver plating on Sheffield plated objects range anywhere from 3 to 10 microns. We did a lot of playing with plasticine and laughable attempts at maths to figure out how we should start off thickness-wise. The only guidance from the literature was that if a copper alloy was 1 to 2 inches to begin with, then the silver layer should be a 1/16 to half an inch. So quite a lot of lack of clarity. So our most successful token ended up with 3.1 microns of silver at most of the points we measured. So we were quite happy about that. It was a little bit thinner than we would have liked, but it was in the realms of tolerance. The token you can see on screen was not our most successful token. This was because we were trying out an approach taken in making makumigane, where you use a torque plate while you're fusing metals. But for us, it really didn't work that well, mainly because our silver was the top layer and just kept sticking to our torque plate. So, tried a second approach, which was just firing the silver straight onto our, in this case, it was actually just a little piece of copper we were playing around with. But the problem with this approach was you would get air bubbles, which then you can see the delamination happening there in the microscope image. And then when you try to roll it out afterwards, you get these really thin patches where your air bubble had been. So the third approach was to poke the silver back down with a graphite rod while you were firing it, which worked really well. And actually, I think is a great example of how craft comes into play, because as you got used to the process, you could see where the air bubble was developing. And if you applied just the right amount of pressure at just the right time, you could just pop it down and it was a great result. You could move your flame around, so you could really finely adapt to where you could see the silver starting to flow too much or not enough. And when you got all of those factors just right, you got a result like the one you can see on the right-hand side there. Of course, that was not the end of the process, but that's all I'm going to talk about it for today, because I suspect I'm burning through my time. So after we made the tokens, they went off to Winterthur, and they carried out all of this testing on them. They basically covered them all with cellulose nitrate lacquers. They also covered a few other things like a pure copper, another type of brass, a glass plate, aged them using UV light, and that is as much as I can tell you about the testing they did, because I am not a scientist. But for anybody who's interested, that's what they did. And those are the results that they got. It was a really small-scale preliminary study, so I think it was actually quite hard to draw any clear conclusions on the basis of the evidence they had. But if anybody is interested, I can pass you along more information about that. So really the key thoughts to take away from this talk. When I first started developing it, I sort of framed it as thinking about the roles that science and craft can play in conservation. But when I got to the end, I actually reframed it to how science, craft and conservation can collaborate as equal partners in the cultural heritage sector, which I think is a small but really important difference, because it's not about people helping conservation, it's about everybody working in cultural heritage together, which then opens up this really interesting sort of field of questions and possibilities of what happens when people from each of those areas are collaborating together, and what can each of them bring to the table, which is what I started trying to do with this diagram over on the right-hand side. And I was trying to figure out what's the unique kind of contribution each area could make, which is actually really tough, because there's a lot more crossover than you might think that there would be at first sort of glance. And the biggest crossover was problem solving, because we're all just problem solving all of the time, which is why I have sneakily replaced magic, which was in the center of this diagram the first time, with problem solving on this image. Because I think it's really important to think about the So, because I think that's what we're all most linked by. And I would love to spend some more time going deeper into all this, but I've probably pushed my luck on time enough. So I'm going to leave things there. If anybody would like to come and chat with me afterwards, that would be really great. This is a developing body of research for me. So any feedbacks or comments would be really interesting. And I've also given you some reading. Thank you.
Thank you very much. That was absolutely fascinating. So are there any questions?
Oh, yes. Forgot about that bit.
Any questions? No? Well, I actually think this is really interesting how you brought in everything. You brought in the actual technical stuff, but also the philosophical, which I think we all need to think about. And we probably do, but don't actually realise that we do it on a daily basis. Like Simon would be philosophical in what he did and the same as you are. So I think that is a really good introduction to how we could start thinking about this. So thank you very much.
Thanks, Anne.
So our next speaker is Georgia Millsom. She's a second-year PhD student here, well, between two institutions actually, because she works in our Imperial's material department and at the Tate, and she's investigating salt formation on 20th-century oil paintings. And in the autumn, she's going to start a placement at the V&A working on a very exciting project, which I don't know if she's allowed to mention, but anyway, it sounds exciting to me. So today she'll discuss unexpected salt formation in 20th century oil paints and share her research into the surprising chemical changes occurring in modern artwork. Thank you.
Thank you very much, Anne. So, as Anne just said, I'm going to be talking about my PhD project titled Unexpected Salt Formation in 20th Century Oil Paints. As I'm only in my second year, there are very limited results. This is just a brief overview of the project in general. So, to start with a little bit of background, when considering conservation challenges within modern oil paints, one of the biggest challenges is water sensitivity. Paintings tend to be unvarnished, therefore dirt can easily become embedded within the paint if regular cleaning is not performed. However, a lot of cleaning methods are becoming water-based due to concerns for sustainability, and these water-based systems are not adequate for water-sensitive paintings. Water sensitivity severity can change across a painting surface, and it can affect a range of pigments. And possible causes of water sensitivity includes poor drying due to thick paint, the presence of metal stearates, and salt formation, which is what my project focuses on. Epsomite is also known as magnesium sulfate heptahydrate, or more commonly known as Epsom salts, and they tend to form white crystalline salts, which are approximately 50 microns long. Their formation is associated with high humidity and elevated levels of sulfur dioxide, and these crystals can cause painted surfaces to become water sensitive, as the salts can disrupt the medium skin of a painting. Moving on to my aims, the overarching aim is to understand the critical environmental thresholds related to salt formation. Essentially, what conditions can we safely keep these paintings in to reduce salt formation, and then apply this to Tate storage and display conditions. This is heavily linked to the BSOP parameters, a set of guidelines that have been released in order to increase sustainability within museums by reducing the reliance on HVAC systems, which control collections in much more controlled environments. So the BSOP parameters have widened these parameters and have said that collections can be kept between 16 to 25 degrees or 40 to 60% relative humidity, unless specific research is undertaken which proves that these conditions are not appropriate for certain collections. Another of my aims is to look at the mechanisms of epsomite formation in two paints, French ultramarine and cadmium yellow. There has been some previous work in this area. done at Imperial, and here I'm going to be detailing 2 master's research projects also conducted in the Department of Materials. Firstly, epsomite formation in cadmium yellow and French ultramarine paint samples aged under varying conditions, such as light and humidity, was investigated. Cadmium yellow and French ultramarine were selected as we know that they do form epsomite and they contain sulfur. So tube paints were painted out, dried for 3 months, and then artificially aged for 3 months, and they were not exposed to elevated levels of sulfur dioxide, as it was theorised that the sulfur present in the pigments themselves would be sufficient for the epsomite to form. It was found that epsomite formed on paint samples exposed to 75% relative humidity compared to the samples aged at 23% and 50%. In 2021, these samples were analysed again to understand what changes had occurred after a year of ambient storage conditions, and it was found that epsomite formation had changed in this year. So this brings me on to my key research areas that I'm currently working on, which is epsomite formation in model oil paints, determining the composition of pigments and extenders, and epsomite formation over time in young oil paints. So epsomite formation in model oil paints. Modern oil paints contain many additives to control the composition and to control the paint characteristics. However, we wanted to investigate epsomite formation in a simplified oil paint mixture in order to understand exactly what was affecting the epsomite formation. So these combinations reflect the key ingredients in paint that we think may be influencing epsomite formation. The oil is consistent across all the combinations, as it's an organic fluid binder that is required to make a paint. The extender is used to reduce the amount of pigment required, as it imparts little to no colour to the paint, and then the pigment is present to impart the colour. The extenders and oils used reflects the composition of cadmium yellow and French ultramarine paints from the 20th century. Next, I'm looking at determining the composition of pigments and extenders using X-ray photoelectron spectroscopy. I'm performing analysis of unaged and artificially aged samples exposed to 60% relative humidity and elevated light, and I'm looking specifically just at the extender and the pigment and ignoring the oil at this point, because the key question I want to answer here is, can epsomite actually form in mixtures of unbound pigments and extenders? I've got some examples of some XPS spectra on the right-hand side. The one at the top shows magnesium carbonate, and the one at the bottom shows magnesium sulfate. So very, very slight differences, but this technique is really good at identifying what's present. Next, I'm also looking at changes in epsomite formation over time in young oil paints, and this relates back to the samples discussed on the previous work slide. So these are the samples that were painted out in 2019. They were artificially aged for 3 months, and they've actually been analysed 3 times post this artificial aging. And there has been significant changes across all these periods in regards to crystal size and crystal shape. And there are differences identified in crystal formation between the 2 pigments, which is what I'm going to talk about now. So these are some microscopy images of French ultramarine paints over time. These are all taken from the same sample. So in 2020, you can identify several cross-shaped crystals, maybe some rod-shaped crystals as well. In 2021, it's hard to see, but there is at least 1 or 2 rod-shaped crystals. But in 2024, I was actually able to identify a wider range of crystal shapes, including an asterisk shape and a diamond shape. So with the French ultramarine, the shapes of crystals remained fairly consistent across 2020 and 2021, but actually a wider variety of crystal shapes were identified in 2024. Now, compared to the cadmium yellow, firstly, the crystals are much larger. In 2020, you can just see a singular rod-shaped crystal. 2021, you can see a rod-shaped crystal with a diamond-shaped crystal. And then in 2024, there's a little cluster of diamond-shaped crystals. And that was kind of the main change that was seen. We're migrating from kind of singular crystals towards kind of clusters of crystals. However, one of the drawbacks of this method that was used to analyse these samples is that although all of these images are taken from the same sample, they're not taken from the exact same spot. So there is the chance that this lovely cluster of crystals seen in 2024 was actually present in 2020, but just wasn't identified. So this brings me on to my further work. So my next steps are to artificially age the model oil paints once they've been dried. I'm going to continue on with my XPS analysis of unbound pigments and extenders in order to answer the question, can epsomite form without the organic fluid binder, the oil? And then to continue the observation of the tube paint samples from 2019 to see if we can still identify further changes and see if we can develop a better method of microscopy. Thank you very much for listening.
Thank you very much. That's very insightful, very interesting. Has anyone got any questions? Can you take a mic up to... Can you put Mark,
it's on,
Mark's
perfect.
mic on?
So this presentation was impressive research. So you're working with dry pigments in your new experiments, and then you looked at what was done before, which was pigments plus extenders plus a binding medium, which was oil. However, in 20th century painting, a lot of the composition is much more complex than that. You have lots of resin, you have lots of additives that may also influence the degradation process. How can we know, based on those models, if those additives, those resins, don't have an impact on the degradation based on this research? Or is it something that you are taking into consideration for the next stage of the research?
Absolutely. This is very much kind of a first step into this area, trying to find out as much as possible. And we've decided to start with this simplified model, and then with the hopes that kind of further projects can go into the more in-depth models where we actually look at kind of representative paint, because the samples from my previous slides, these samples are the tube paints, so they will contain all the additives. So we know that the additives may, it may have an effect, yes. We know that tube paints do form the epsomite, but we just decided to kind of take a step back, see if we could understand what's happening in a simplified paint mixture first, and then build up the complexity once we've got an idea of these mechanisms.
Thank you. Any more questions? Just one. One more or what? No. We need to move. Okay. So sorry. Okay. Well, thank you very much, Georgia.
Thank you.
Okay. Just a spot of housekeeping there. Marc, you're on next. Marc is Head of Heritage Science Conservation Research at the National Archives, and will present on exploring the ageing and reversibility of heat-activated tissues for water-sensitive archival materials.
Thank you very much, Anne, for the introduction, and I'd like to thank the organizers for offering me the opportunity to present some of the research we're doing at the National Archives on the heat-set tissues. And while I'm actually here presenting today, most of the research I'm talking about is something that has been done by a colleague of mine, Karina Levings, who is in a much better situation than me here, because she's actually in Australia. And she sent us a couple of images from with a beautiful blue sky while we're here in London with a beautiful gray sky. So to start with, I'm going to talk quickly about what is heat activity tissues and what they are used for. Heat activity tissues are a repair material that are composed of a carrier, which is often Japanese or Western tissue, and a polymer coating, which is activated by heat, and heat activity tissues. It is used a lot on post-1950s modern wood pulp papers, as well as mold-affected documents, or any actually items that cannot be exposed to moisture. And they find lots of application in archives and in library collection because they are very quick to apply, and they do not require any drying time. And so that made them very useful for a long time within TNA. And so in between the 1950s and the early 2000s, they were widely used to stabilize a lot of fragile documents, which often led, and I'm presenting here an example of a Titanic ledger, which has been completely lined with heat-set tissue using a heat press. So as you can imagine, this is something that in modern days we don't really like to do. We want to be a bit less invasive. And on top of that, it also comes with a couple of pitfalls which are often seen in discoloration, in embrittlement, and poor reversibility, which in the early 2000s led to discontinued use. However, more subtle use of heat activity tissues remained for example, our numerous large-scale digitization projects, as well as for their use on modern wood pulp papers. And so this is when this research kind of came along. So currently, we are using gelatin-based or wheat starch paste remotionable tissues. But the thing is, when we apply them to some of our paper, and I'm showing here a choice of 4 papers, which are color choice, newsprint, wax paper, and tracing paper, which is a good representation of the types of paper a lot of the conservators are working with at the archives, you will see that a lot of wrinkling do form. So it kind of shows that this is a type of material that might not be well adapted to our needs. And so this is when Karina looked into potential alternatives, both in-house made as well as commercial, looking at those 2 Lascaux-based tissues, like adhesives, an aquazole, and then 2 commercial alternatives that were used at TNA in the past. We worked on the same 4 papers that I talked about before, which represent a good kind of array of documents we would work on at TNA. And then application is with a heated spatula. So we looked at 3 aspects. One of them was the color change over time. The other one was the reversibility. How much can we actually remove upon application and after aging? And the workability, or like how it's handled by the conservator. However, the first thing that we looked at was the blocking. So blocking, and I had my notes because I always kind of forget exactly. It's the unintended sticking of materials after it's been kind of stored together. So what it would happen in a book or in a stack of papers. And so in order to look at that, nothing very crafty, but Karina created a block of newsprint paper with the different types of adhesive we were looking at, put that under a 1.8 kilo glass weight into the aging chamber for 4 weeks at 75 degrees and 65% humidity. And after a month, she kind of looked at what was happening when she tried to open the pages. And by doing this, she looked at how much lifting happened, if there was any sticking of the pages that happen between the various types of materials. And so she was able to say that the various coats of Lascaux material ended up making the pages stuck together, skinning of the paper upon separation. Aquazole and Crompton paper were not great. There was a bit of sticking, but it was not too bad. And then Filmoplast, the last one, didn't have any issue. So in that case, Filmoplast 1, the rest of them 0. Looking at the color change, again, she looked at the paper before and after aging. And so you can see there are definitely some color changes happening. There's also some color change between on the paper between before and after aging. So we also took that in consideration, and then we measured the delta E. So 1.5 is basically, a delta E of 1.5 is basically when we start seeing a color difference. And so we drew a line at 1.5, and we looked at whatever arrived on top of that. And so you can see that some of the heat-set tissue didn't really make the cut, with, for example, the Crompton one being always in the red. Some of the one we are actually using also in the red. And so here, the Crompton, Filmoplast, and the 4-coat of Lascaux didn't really make the cut, but Lascaux 1 and Aquazole were always kind of below 1.5, so it was pretty good results. So then reversibility. So she looked at how much can be removed first mechanically using a spatula, and then also chemically using ethanol. And I'm not going to go into detail of those tables, but what's interesting is that before and after aging, you have a lot of mechanical removal that just doesn't work. You have lots of fails in here, a few in here, and then after aging, well, chemical reversibility is pretty effective in both cases. However, interestingly enough, again, Filmoplast had a good reversibility both before and after aging, both mechanically and chemically, which was a very nice and unexpected result. So again, Filmoplast 2, the rest kind of lost count, but I'm guessing 1 for them, 0 for others. But Filmoplast seems to kind of take the lead over here. But it's one thing to kind of have a feel that it's removed well mechanically, and you can see here, like we removed the bottom section, and then you can see the amount of the courier over there. But are we sure there is no more adhesives in this area that have been kind of removed? And so in order to assess this, we turn to FTIR, because the beauty of those materials when we look at them in FTIR, that they have those 2 bands over here that kind of fall when there is no band for the paper itself. So it's a good way to assess if some of those materials remain on the paper itself. And so if I give an example here of the Aquazole and the Lascaux, you can see before removal, you have a pretty big peak here. After removal, it's very small, and then same over here for the Lascaux, you have a massive peak here, and then very, very little after removal. However, that kind of already shows that even though it seems to be removed, there's still a little bit remaining on the paper. So it was interesting to already have this. So those are results from last week. So we still are trying to figure out the best way to show them, but I try to show them here as a percentage of what remains after removal, which also already kind of show some of them performing much better and other performing much worse. And so, for example, the Crompton, as you can see, seems to be very bad in both the newsprint and the tracing paper, as well as in the color choice. This does perform well with the wax paper, with the Aquazole being so bad. However, Lascaux, again, performed quite okay in a few papers, which seems to be a trend over here, which is, again, very interesting and somehow unexpected because we stopped using it a while ago. So then it's one thing that we get good results in the lab, but I think when it comes to this, it's important that the conservators are also happy to work with them because they are the one making the choice of using them every day. And so we had a workshop at TNA, and one of the conservators for the large GG project came to Karina. I was like, oh, it would be amazing to try to test them in real life with the types of objects that we are using and that we're treating every day. And so she tested a series of substrate, and she looked at the ease of application, the visual properties after application, and the removability mechanical after 5 hours. And again, here you can see Lasco did perform very well, outperformed what we are currently using, which was also very interesting. And seems to kind of, when you look at that, Lasco is pretty much everywhere. So it was very interesting to see that the chemical aspect related to like the craft as well, from the science to the use in the studio. She also looked at the media lifting, so whatever was removed when you would remove it. And again, Lasco did perform very well. So we had some lifting for red crayon for Lasco with nothing happened in any other, when the one we're using currently, so the gelatin and the wheat starch paste, did perform the worst. So again, quite an interesting result, given that we decided to stop using those materials like 20 years ago. I'm gonna go quickly, well, actually not gonna be talking about the application. I think this is another one where the Lasco kind of shows that very well. But I'll just move quickly to the summary. And I think here, it's a summary of all of what I've talked about today on all of the heat-set tissue we tested. But I think what's important to note is that there is not a solution fits all. I think even though Lasco did work very well in most of the cases we looked at, it also performed poorly in some of the papers. So I think it's important to understand that what will work for one paper will not work for the other. And I think this is when those research where we kind of put together the scientific aspect with the day-to-day workability and observation of someone that is the craft person at the end of the day is an important way to kind of understand the materials we're working with and understand the offers that are over here that we can kind of put in action in one case but not in the other. So I think this is the beginning of the research. We'll still have much more to do on that, and more is coming. I think there are some aspects that we would like to kind of investigate further, the impact of the heat that is being used to apply, how much are the adhesive going into the paper, but this is something, for example, that we cannot look at TNA. We don't have the instrument for that, so it's something that we hope to be able to do in the future. And I think I'm getting close to my time, and so with that, I would like to acknowledge all of my colleagues at TNA, and especially Karina, right over here, who is probably thinking of us while she is sunbathing in Sydney. And all of you for your attention. Thank you very much.
Thank you, Marc. That's most thought-provoking, particularly as I'm an archivist and I have all these problems myself. I can tell you about that another time. Anyway, there's one question. You have time for one question. Yes, down here. Oh.
It's a long way to get the microphone. Thank you so much. Very interesting talk. I had a question on the percentage of removal that you've been measuring. I imagine that's based on the FJR results that you've done. What did you use? Did you put a reference inside, or is
so what I used ratios. So we integrated various bands. So we integrated the bands for the one I showed for each of the heat-set tissue, and then we integrated the bands of the cellulose, which seems to not kind of fall too much into it, especially after removal. And then we had normalized all of our data beforehand so that I considered the integration of the big peak before removal to be 100%, and then I looked at how much the ratio was after removal and did a calculation to kind of get that as a percentage. There might be much better ways to do it, but that's what I kind of came up with on Friday before having to send this presentation
No, that's good, because I was
to
thinking
the organizers.
if you had any pressure, you were controlling any all the setups that you were using when you were doing it, because I imagine you did the ATR.
Yeah.
So yeah, okay, cool. Thank you.
Thank you. Good thinking on your feet there, Marc. So please thank Marc again for his interesting talk. And our next speaker is David Thickett, Senior Conservation Scientist in Collections Conservation at National Heritage. And he's going to present on the GoGreen project and Reach's infrastructure. Thank you, David.
Okay, as you can see, my title's a little longer. I can see why it got cut. But just so as you think I'm just talking about the overviews of the project, I'm going to be talking about analysing deterioration rates for individual objects and their stability. And we're just being able to do this. Instrumentation's developed far enough we can do it. We know enough about the degradation for some materials. But why do we want to do it? My team is very much involved in research in preventive conservation. Preventive conservation is managing the degradation rates, not making them zero, and being able to measure them is really fundamental to that, and also to some of the other research that we do. And I'm going to show you some examples from the GoGreen project, a Horizon project we're involved with, and talk a little bit about the Reach's infrastructure, which will hopefully allow this to be applied in other places. And I'm going to talk about enamels and glass. And this is a Limoges enamel. It's low melting point glasses on a copper plate. It belongs to the Verner Foundation. It's on long-term loan to English Heritage, along with about 120 of its compatriots. And for those of you that know about glass degradation, the blue panel here and the purple panel here of glass show obvious signs of chemical degradation. They're not as translucent as the surrounding glass. They're now matte as opposed to gloss. And this is a reaction of the water vapour, and it can be other chemicals in the air, with the glass, and it's pulling the sodium and potassium out of the glass onto the surface and leaving a thin altered layer, sometimes called a gel layer, on the glass surface. And we wanted to look at how quickly this process was happening in some of our environments. And the way we've looked at it is with FTIR, with a microscope. This is the British Museum's FTIR microscope they very kindly let us use. And this is a much younger me looking at silver tarnish, silver lacquer, about 30 years ago. But the microscope, we can bounce onto the surface. We need to take a lot of care getting the microscope point, which is 100 microns in diameter, back to the same point on the surface. And we've already heard about the issues with that. We also need to take care about the long-term stability of the instrument, because thankfully a lot of this degradation takes quite a long time. But you need to have standards to make sure your instrument is staying the same. This is the sort of data that we get out, and the red peak is undegraded glass. It does have a shoulder here, and as the glass gets more degraded, that shoulder becomes a separate peak. And other people's work has shown that the distance between the two peaks in terms of peak position is related to the thickness of this degraded layer. And as it happens, with infrared spectroscopy, peak position is much, much easier to measure than area under the peak or height of the peak, and much less influenced by reflection effects in the way that we're doing the measurement. So these are the spectra. We can measure this. We need to measure 16, 17 spectra per area of glass, because it is variable across the surface. And this is the sort of results we get for the blue and purple glasses that are unstable, and you saw there. So in 2004, we had a measurement, and there is splitting. There's definitely degradation. We went back about 4 years later to the BM to do this, and we're quite horrified to see the splitting has definitely increased. So as we knew there was something wrong with the preventive conservation, we needed to change it. The target we were using at the time was keeping the RH below 42%, and this is the percentage time above 42%. So as we weren't doing a great job in 2008, we changed the silica gel for a much more effective one. We did a better job, but it's still increasing. We then took the decision to put a machine into the showcase. We managed to keep it below target, and it's been flat. It was flat up until 2019 when the machine had to be scrapped because it could no longer be repaired, which is an issue with these kind of studies. Okay, so that's chemical degradation. The more spectacular thing that can happen to enamels is if you get a big change in temperature, you can have pieces of the enamel really pop off, and they can travel quite long distances. We've seen pieces of glass 2 meters away from the actual object when this has occurred. This is a failure of heating. The temperature dropped to 10 degrees C overnight, and unfortunately, quite a few pieces of glass came off. From a science point of view, having pieces that you can analyse is really, really good. So they were going to go back, but we could put them in an environmental SEM first, and this is what we see. Here we see the gel layer at the top, the altered layer, and that's about 30 microns thick. You may not be able to see, but believe me, there is a very thin altered layer on the bottom that was against the silver, and we do have salts under there. And what this means is air must have been getting underneath the glass. And if we look at the silver here, part of it's still quite shiny, some of it's blackened due to tarnish, which we've heard about. That means air was getting underneath. It had become debonded. And that's a big problem and a known problem with enamels. But the thing is, it's really, really hard to follow. Because even if you look at a microscope through the glass, it's really hard to know where the glass is still attached to the metal or not. And about 20 years ago, we used a technique called acoustic emission. It was the first time that we'd used it, and it was a very steep learning curve. But essentially, when rigid materials deform, you have micro cracking. Cracking that is way below what you're ever going to see with the naked eye, hopefully. You also get macro cracking, as we've seen. And with a high sensitivity, high frequency piezoelectric sensor, you can pick this up by pushing it against the surface, which is what we've got here. We've got the sensor and a sheet of Melanex that we found actually is a good couplant to the glass surface. And we had a bit of space to put this into the showcase. And depending on the background noise, which turns out to be the really limiting factor, you can perhaps detect cracks that are a fraction of a square micron in size being formed by this technique. Actually, probably a little bit better with glass now, we think. These are the sort of results. So this is the temperature going up in the showcase. So this is the lights being turned on, which generates an enormous electromagnetic burst. And as the temperature goes up, we can see we're getting acoustic emission, expressed in terms of hits here. But what we've, the other thing we measured simultaneously is the deformation of the plates. They're slightly curved, and we used a laser to measure that, and we had enough space. And you can see as the temperature goes up, the plate deforms, and how that deforms. And then, as we did enough acoustic emission on enough objects, we began to get this sort of data. For cracking, actually, the energy is much more useful than the parameter called hits. And what we found is if we keep the daily temperature change below 2.35 degrees C, we don't see any acoustic emission. Once it gets above 2.35, it increases, and it increases as that temperature fluctuation in a day increases. Now, we cannot keep our buildings below, with a daily fluctuation below 2.35 degrees C. It's possible with air conditioning, but it is very expensive. So this fit gives you some idea of how much damage you're going to be getting if you don't make that figure, which, as I say, we almost always can't. Oops. Okay, we've also used this technique with wooden furniture. And wood is damaged by fluctuating RH, which is what we normally really worry about. And within historic houses, it turns out that actually pieces of furniture often are the most sensitive thing there. They're generally more sensitive than paintings because you've got different types of wood at different anatomical directions and they're restrained. And here you see temperature, relative humidity in the room. This is the acoustic emission off of the card table. We've also done it off of the piano. And you can see we get this highly separated temporal data. And we can start to try and fit the acoustic emission that we're seeing here with what's happening with the relative humidity. Is it related to this drop in relative humidity? But we can start looking at the data. We've done quite a number of objects now. There's a couple of other examples, and we're getting better at pulling the data out of the general noise, which I'm not going to talk about how we do that. And the other thing we've been able to do is look at different types of modelling or damage functions for the wood. And a number do exist. This is IPI's Dimensional Change Index. This is the Climate Toolbox by Boris Pretzel. This is the restrained wood module on the Heavy E platform. And what we can do is feed in our relative humidity data, get the model to predict how much cracking should occur and when it would occur, and then compare that to the acoustic emission data. And for individual objects, you know, IPI 67% of where we saw acoustic emission it predicted, Climate Toolbox higher, Heavy E slightly higher. And if we aggregate that across 22 pieces, you get quite a good portion. And the Heavy E is performing extremely well, probably as well as we could ever hope, for modelling a very complex thing with a simplified approach. But what's really nice about this is it makes the work transferable, because acoustic emission is expensive. Each one of those bits of kit probably costs £10,000-20,000. It's not something a lot of people are going to use, but anybody can put their temperature humidity data into Heavy E and get a prediction, and we seem to have reasonably validated it, at least in the terms of those objects. Okay, it's the first part over. So we've done a lot of work on energy use and carbon reduction, and we think we've reduced it by over 40%. Part of that is what I've just been talking about, understanding the conditions we need to achieve, not what's desirable. And the second thing I'm going to talk about is analysing an object to determine whether it's stable or unstable. And we've been able to do this with a number of objects. I'll talk about glass. And what I mean by that is generally within preventive conservation, we group types of objects together. So as we say, I'll keep our panel paintings at 45 to 55. It's a subset in Bezo. Can keep the canvas paintings a bit wider, but we assume they're all the same. And anybody that's worked with a collection that has deteriorated, and all of them deteriorate, will soon know that some objects do, and sometimes an object right next to it that looks very similar doesn't. And if we can pull this out, it can help us. And just note with glass, for most glass, it's relatively stable, and people have said, well, the most common reference says 40 to 50%, but the unstable glass, which is maybe 10%, it's saying 40 to 42% relative humidity, which is achievable, but extremely difficult. Okay, so first example with this is archaeological iron. Analytically, it's a horrible thing to try and analyse. There's loads of different compounds, and what we're really interested in isn't happening on the surface, it's often underneath the surface. But what you can do is just look at oxygen depletion. So as we put an object in a sealed vessel with something to control the relative humidity and just measure the oxygen level. And there's really neat modern meters that just have a sensor in there that you shine light on, and to do with fluorescent quenching, you can say there's 21% oxygen in there, or 15, or 20, as it goes. And we found 4 behaviours. There's 3 groups been working on this. We've probably done about 5,000 objects now. There's the stuff that is green, where it really doesn't deteriorate under any of the RHs that we can, even we, English Heritage, can subject it to 80%. Which is great. You don't have to do any preventive conservation. And that, we think that's about 65% of our collection. Most of the material follows this red line. Nothing below 16%, slight increase at 30, big increase between 45 and 55, depending on the temperature. And then we've got some material from anoxic sites that doesn't react until later, and thankfully a small amount that reacts very, very early on. But by being able to place an individual object into one of these groups, we can then tailor the preventive conservation for those objects that need it. And if it only doesn't need anything, we don't need to do anything. And there's some other advantages, which I can talk about if people are interested. And there's really 3 ways of doing this. We published a paper a couple of years ago. There's determining the composition if we know enough about it and we can do it. There's measuring the deterioration rate, which I've just shown you, which works well for copper and iron archaeology, but microfading's quite a common technique. That's another example of this. And then there's what's probably more complex, or you need to know more, is determining the state of preservation or markers of damage. And I'm going to talk about weeping glass for this. And just to say why it's important, this is just some experiments looking at different machines to control environments in showcases. And the important thing is the amount of energy goes up quite dramatically if we try to keep it this tight compared to if we don't. And if we look at the embedded carbon and the lifetime, again, it's much, much higher if we try to keep it at the 40 to 42 as opposed to the 40 to 50%. So as we know why we're trying to do it. And I mentioned composition. We know with glasses, there's been a lot of work on this, that if you put the composition onto a ternary diagram like this, if the points fall into the red region, it's going to be unstable. If they fall into the paler region, it's going to be stable. So you could analyse your glass, and for archaeological glass, you can quite easily take a piece off, do a cross-section, analyse it in the unchanged glass. But this alteration layer changes things like X-ray fluorescence because it's got to get through this before it gets to the glass. So for art glass, we can't really, or you will not have a very long career in conservation science if you go to your curator and say, do you mind if I just nip a piece off the end of that 14th century vessel or Limoges enamel? So what we've done is looked at 2 sets of glasses. The Limoges enamels you've already seen. They're potassium glasses. They're very degraded. The gel layers are certainly in the tens of microns in size. And then a series of sodium glasses. These are daguerreotypes of Darwin and his family. They have a glass plate, and these are more stable, and they've only been around for about 150 years as opposed to 700 years. So the gel layers on those are between about 0.1 and 0.5 microns, and we've already done the measurements. And then what we did is we took instruments that are available in the larger museums now and tried them on the 2 types of glass to see if we could detect deterioration. So it's FTIR, the BM's microscopes are dead and buried. They've probably got a much nicer one, but a lot of places now have these Booker portable units which can do an in situ analysis without taking a sample. And again, you see the 2 peaks, so they certainly work. The problem is our glass degradation layer is very thin, and this analyses about 1.2, 1.5 millimeters of the glass. So you can't really see the degradation from the sound glass. There's a way around that, which is attenuated total reflection. Particularly if you use a germanium crystal, you're only going to analyse about half a micron of the surface. It works on a microscope, and it works really well. And this data is actually from that microscope, which is at the V&A. And that worked well with both glasses, the enamels and daguerreotypes. We looked at another type of spectroscopy. This is near-infrared spectroscopy, a method developed by the Smithsonian, looking at this peak with this calibration. And again, it works with the more degraded, but this is pretty flat down at the bottom end. It's not really good with this just beginnings of degradation. I mentioned the sodium and potassium coming out, and that sits on the surface or is weakly bound inside the alteration layer. And if we can get it off of the surface, and we need a method to do this, we can put it through ion chromatography and see how much is there. And that's a really good way of detecting how much sodium in this case, or potassium, has come out. Okay, so just to summarise those, everything worked with the more degraded glass, including Raman and OCT, which I haven't talked about. Only really the germanium ATR and the ion chromatography worked with the early signs of degradation. And ideally we want to catch this early, because once it's gone to a certain point, once the alteration layer is thick enough, it will crack with temperature and changes in relative humidity. Okay, so to conclude, we've already said this, there is certainly some exact uncertainty about the exact instability borderline with glasses of different compositions. And within GoGreen, we hope to address some of that by making, we've got 6 or 7 compositions we're using in the project. We'll artificially age those, get different layers, different alteration layer thicknesses, look at the different techniques, and part of the output of the project will be to develop a series of technical notes to allow other people to do this analysis in their labs. Actually, go back there. Ah, okay. Oh yeah, I did. Sorry. And if you are interested in GoGreen, there's the website there. It's a project of 4 parts. This is one small part of it. We're looking at new materials and also education. And my final slide is Richards. We've been lucky enough to be awarded Richards funding to build a lab to do this, but also take it to other people. So we've got a suite of fixed and portable equipment and a number of very good partners. And from the end of 2026, you should be able to apply to have us come and do this kind of work on your collection. And I'll finish with that.
Thank you very much, David. That was really interesting. Thank you very much. Very technical, but that's fine. Any questions? One question, I believe, we can have.
And don't worry, if we come, we'll do it and we'll interpret the results. You don't need to know any of this.
Well, you can talk to anybody during the break, which we're going to have now for lunch. But there's one other thing that I need to say, that there's been a video up about the Royal College of Science replacement war memorials, which was a project I was involved in. So we've got some stonemasons to clean up one which we found in somewhere which we should have known it was there, and in a basement of another building which had been refurbished, so it's a bit weird, and then a new one completely made to replicate the first one that was completely lost. And so this has been playing on a loop, but if you want to actually look at them, you can meet me by the technicians' posters in the entrance hall after you've had a quick bite to eat. So I'd just like to thank all our speakers for this session, and thank you all for listening, and please go and have lunch.